Okay, hello everyone, and welcome back to the Latin American webinars on physics. I'm Joel Jones from the PUCP in Peru, and I will be your host today. This time we have Julia Gehrlein as a speaker, who is an assistant professor at Colorado State University in the USA. Julia carried out her PhD at Universidad Autónoma de Madrid in Spain, having later been a research associate at Brookhaven National Lab in the USA, and then postdoctoral fellow at CERN. So for this webinar, which is the 177th one of our series, Julia will tell us about neutrino factories, and we're very happy to have her as a speaker today. Before we begin, we remind everyone that you can be part of the discussion, writing questions, making comments via the YouTube live chat system. So now I'll hand you over to Julia.
Okay, thanks a lot. It's a pleasure to be virtually with all of you. Today I'm going to talk about neutrino factories and their physics potential. Okay, so this talk is for sure about neutrinos. So first, where do we actually stand right now in neutrino physics, starting with neutrino oscillations? Since the discovery of neutrino oscillations in 1998 and 2002, we have learned a lot about neutrinos. We know they do change flavor. This is the effect behind neutrino oscillations. And this comes from the fact that the flavor eigenstates and the mass eigenstates of the neutrinos are not aligned. This means when neutrinos travel over a long distance, they will change their flavor, they will change their type. And the probability on which this flavor change depends in turn on 3 mixing parameters as well as 2 mass splittings. Out of these 3 mixing angles, we have measured 2 of them with very good precisions. These are theta 1,3 and theta 1,2. We have also measured theta 2,3. However, there is still some larger uncertainty here. We don't know if theta 2,3 is larger or smaller than maximum, where maximum being 45 degrees. We also know that there are 2 different mass splittings in the neutrino sector. One of them, delta M21 squared, we know is small, is of the order of 7 times 10 to the minus 5 eV, and we also know its sign, we know it's positive. For the other mass splitting, which is delta M31 squared, we only know its absolute value. It's around 2.5 times 10 to the minus 3 electron volt squared. Furthermore, the other mixing parameter which plays a role is the CP phase delta, and as you can see here, as of now, we have not measured this parameter yet. Its 3 sigma range is basically between 0 and 2 pi. However, future experiments are going to measure the value of this phase delta. They are going to measure the the sign of this mass splitting, and they are going to make more precise measurements of theta 2,3. However, a parameter oscillation experiments are not sensitive to is the absolute neutrino mass scale and the nature of neutrinos. So from this plot here, you see that only the difference in the masses squared play a role in neutrino oscillations. However, the absolute neutrino mass scale, which is what is the mass of the lightest neutrino, is inaccessible at oscillation experiments. So we have to look at a different kind of experiments to measure the absolute neutrino mass scale, and the experiments we are looking at are cosmological observatories as well as beta decay endpoints spectrum measurements. Currently, the strongest bound on the absolute neutrino mass, and actually the sum of all of the neutrino masses comes from cosmology, which tells us that the sum over the 3 light neutrinos has to be smaller than 0.0272 eV. However, this bound depends a little bit on the data sets you are combining, but we have very strong bounds right now. Concerning the nature of neutrinos, the most experimentally feasible way to test the nature of neutrinos is a process called neutrinoless double beta decay. This is a process where inside the nucleus, two beta decays happen simultaneously, and if neutrinos are Majorana particles, which means they are their own antiparticles, the two neutrinos will not get emitted from the nucleus, and you only see the two electrons coming from this double beta decay. So far, this process has not been observed yet. And in this plot on the right, I'm showing you the available parameter space for the observable neutrino-less double beta decay, the particle physics observable, which is m beta beta, which is also different in the inverted ordering as than in the normal ordering, where normal ordering refers to a mass ordering of the neutrinos, where the lightest mass is M1 and contains the most amount of electron neutrino. In inverted ordering, the lightest mass is M3 and contains the least amount of electron neutrino. So you see these two different bands depending on the mass ordering, and you also see on the x-axis here that the parameter space depends on the lightest mass. So here you have some constraints from cosmology, and then on the horizontal constraints, these are from neutrino-less double beta decay from the non-observation. Then we also do neutrino scattering experiments, and we have measured the cross-section of neutrinos across many orders of magnitude of neutrino energy at low energy. As of a few years ago, for the first time, coherent elastic neutrino nuclear scattering, or SEVENS, is detected and is actually on its way to precision physics, but also at GeV energies, TeV energies, and even higher energies, we have seen neutrino nuclear scattering and could determine its cross-section. In particular, at some GeV energies, this uncertainty on the cross-section is actually one of the limiting factors for future accelerator experiments. So there is still a lot of experimental efforts as well as theoretical efforts going into calculating and measuring these cross-sections. But also, neutrinos can provide a portal to physics beyond the standard model. So first of all, the fact that we have seen neutrino oscillations, which implies that neutrinos have a mass, goes beyond the standard model of particle physics, where neutrinos are strictly massless. So massive neutrinos are already new physics. Additionally, there are some persistent anomalies in neutrino physics. For example, this low energy excess of mini-boon and LSND, as well as something called the gallium anomaly, persist in neutrino physics, and a vanilla explanation of just adding one more neutrino, a sterile neutrino, do not provide a good global fit to all of the neutrino data we currently have. However, so far, there is no convincing standard model explanation of these data sets either. So this remains a mystery, and we hope to be able to find an explanation with future neutrino experiments. Additionally, neutrinos can provide a portal to physics beyond the standard model. The first portal is directly the neutrino portal, so we can introduce sterile neutrinos, right-handed neutrinos called here NR, and couple them to the Higgs doublet and the lepton doublet, and this provides then an interaction between the active neutrinos and the sterile neutrinos via the neutrino portal. But neutrinos could also interact with new vectors or scalars beyond the standard model via new neutrino interactions, and these new particles could either couple to the standard model via the scalar portal, via mixing with the Higgs, or via this via this operator, via mixing with the photon and the Z boson. Additionally, in the past decades, the field of particle physics has realized the benefit of neutrino experiments not only for neutrino physics, but also for dark matter physics, for axion searches, for astrophysics. And here on the left, I show recent constraints from the microboon neutrino experiment, which with its data could also constrain the existence of some scalar dark matter candidate in a certain mass range. And here on the right, I show a picture of the Milky Way from IceCube in neutrinos, in addition to a picture of the Milky Way in gamma rays and optical light. So there is a lot of complementarity from neutrino experiments and from neutrinos, which are relevant for other areas of particle physics. So where are we going? In terms of oscillations, we have a rich program. Upcoming long baseline accelerator neutrino experiments, Hyperkamiokande and DUNE, are going to measure the CP phase. They're going to measure the octant of theta 2-3. They're going to measure the mass ordering, which corresponds to measuring the sign of delta M31 squared. We also have an upcoming medium baseline reactor neutrino experiment, Juno, which will measure the solar parameters, which are theta 1,2, delta M21 squared, as well as the mass ordering. And then we also have atmospheric neutrino experiments, Hyperkamiokande, IceCube Gen 2, neutrino.HK, which are going to measure the atmospheric parameters, more precisely theta 2-3, delta M31 squared, as well as the mass ordering. In particular, in combination with Juno, we are going to get a very, very precise, very significant measurement of the mass ordering, as well as from these accelerator experiments. So the future of neutrino oscillation physics is bright. There are a lot of upcoming experiments. But also experiments which are going to measure the absolute neutrino mass scale and the nature of neutrinos are moving forward. Indeed, future cosmological observatories will measure the sum of the neutrino mass, maybe already very soon, as they see result on the sum of the neutrino mass is already very close to what we expect to see minimally. And because our expectation for the minimal value of the sum of the neutrino mass is different in the normal ordering versus inverted ordering. If we get a measurement of the sum of the neutrino mass, which is only consistent with one of the mass orderings, we can also measure the mass ordering from cosmology. Concerning the nature of neutrinos, future neutrinoless double beta decay experiments aim to probe this inverted ordering region here completely, but also from the theoretical point of view, there is some progress on the nuclear matrix element calculation, which is needed to extract the observable in experiments, which is the half-life of the isotope, to translate it to M beta beta. And yes. Okay, so concerning scattering, there are new upcoming experiments which will refine our cross-section measurements at TeV energies. Phaser at the LHC and SHIP will both measure the cross-sections of neutrinos and tau neutrinos, in particular for SHIP, more precisely at these TeV energies, at very high energy, ultra high energy. IceCube Gen 2 will measure the cross-section of cosmic neutrinos more precisely. So overall, the error bars in this plot are going to shrink in the near future. In terms of BSM physics, upcoming oscillation experiments will probe BSM physics, the existence of a sterile neutrino, for example, at DUNE, or the existence of new neutrino interactions called NSI, as well as DUNE, what I show here. There are also dedicated experiments. The short baseline program at Fermilab is set to test these experimental anomalies we saw in Minibune. So we are going to learn more about that in the very near future. But the question is, what's next? What do we want to do after this next generation of neutrino experiments? So the answer depends on the outcome of these experiments. If they find new physics, if the results agree or disagree, and the general landscape of particle physics. And the question is, what do we want to learn about after this next generation of neutrino experiments, after DUNE, after the short baseline program, after these cross-section measurements? So there are different answers to that. There are a couple of proposed oscillation experiments, for example, T2HKK, which is a T2 hyper K, but with an additional hyper K-like tank in Korea. ESS and USB, which is the idea to use to produce a very intense neutrino beam at the European spallation source in Sweden, and then place a Cherenkov detector at some very long baseline in Sweden. Both of these two experiments will be able to probe the second oscillation maximum. A proposed experiment which could improve our sensitivity to low energy neutrino physics, MEV neutrino physics, is the FIA detector, which is a water-based liquid scintillator detector, which could be the fourth DUNE module. But so far, these are just proposed experiments, very interesting, but no decision has been made yet. What I'm going to talk about today is a different possibility for a future neutrino experiment, and this is motivated by the recent P5 report, which mentions a muon collider as a possible future collider. And it also mentions that this upgraded facility needed for a muon collider could also generate a neutrino beam, which brings natural synergies with studies of neutrinos beyond DUNE. And what they're talking about is the concept of a neutrino factory. So a neutrino factory produces a neutrino beam from the decay of energetic muons, and this could also be the first step towards a muon collider, because this is exactly the particles you are colliding in a muon collider. So a neutrino factory has already been considered more than 20 years ago in the early 2000s to measure CP violation for a very small reactor mixing angle theta 1,2 smaller than 1 degree. However, we have actually measured theta 1,3 to be of the order of 8.5 degrees. So it's actually not as small as we initially thought. And now, due to the renewed interest in muon colliders and our improved current knowledge of oscillation physics, a modern study of a neutrino factory is actually timely. There was the non-oscillation case of a neutrino factory has recently been studied in this publication. So now I'm going to focus on the oscillation case in the following, and I'm going to talk about two papers. In the first paper, we looked at the standard three-flavor oscillations. In the second paper, we looked at new physics in oscillations at a neutrino factory. So the goal of a neutrino factory as a successor of DUNE and Hyper-K and Juno and the future atmospheric neutrino experiments are not to discover CP violation. We assume that DUNE and Hyper-K are going to do an excellent job in measuring the value of the CP phase. But the goal of a neutrino factory could be a precise measurement of the mixing parameters and/or potentially resolve any discrepancies identified in previous measurements and resolve the degeneracies between standard oscillation parameters and new physics upcoming experiments might suffer from. So our setup is to assume that DUNE and Hyper-K are going to be successful. They're going to bring the measurements they set out to do. The question is, what else would a neutrino factory actually add? For this reason, we're going to study the precision on the oscillation parameters combining DUNE, Hyper-K, and a neutrino factory, and study the expected constraints on new physics scenarios combining DUNE and a neutrino factory. And then we are going to compare the results to DUNE and Hyper-K only, with their nominal running time as well as some increased running time, which will tell us if a neutrino factory is just going to add more statistics or is really bringing something systematically different to the game. We are going to use the GLOBES framework for our analysis to answer the question what the added value of a neutrino factory is to our picture of neutrino oscillations. So again, the setup for a neutrino factory should look like this. So the neutrinos get produced in the decays of muons and antimuons, which decay just in the standard model into two types of neutrinos and an electron. So you have a muon storage ring, which looks like a racetrack design. And then along the straight path of this muon storage ring, the muons will decay and you get a very energetic, a very collimated beam along these straight lines of the racetrack. since you have to angle the muon storage ring a little bit down just because of the Earth's curvature, we expect some long baselines. One of the neutrino beams is going to be pointed towards the far detector. The other neutrino beam is kind of shooting in the sky, coming from muons decaying along this direction of the muon storage ring. This is just a kind of a setup which has been discussed some more than 20 years ago, but the essential point is you need some setup to accelerate the muons and then some setup for the muons to decay. Okay, so what is the difference between neutrinos from a neutrino factory and neutrinos from fixed target accelerator experiments? So the achievable maximum neutrino energy is higher at a neutrino factory. And this is shown here on the right, where I'm comparing the flux from DUNE to the flux from a neutrino factory, assuming the muons have an energy of 5 GeV. The composition and the expected energy of the neutrino beam is well known. We know that we are going to get muon neutrinos and electron neutrinos because it's just a 3-body decay, and we know the muon neutrinos will have a maximum energy of the muons. And we also get equally many neutrinos as antineutrinos, albeit of different flavors. You get muon neutrinos and anti-electron neutrinos, or electron neutrinos and anti-muon neutrinos, depending on muon decay or anti-muon decays. Which also means we have a large amount of electron neutrinos coming from the source, which allows us to look for muon neutrino appearance searches where electron neutrinos have oscillated into muon neutrinos. But we do not have any tau neutrinos in the source at all, which means we do not have an intrinsic background for tau neutrino appearance searches. And finally, the neutrino energy is tunable and flexible just by tuning the muon energy. So the setup of a neutrino factory we have in mind is we want to make use of existing infrastructure, which means existing infrastructure for an accelerator as well as the far detector of the oscillation setup. So we look at 2 different setups. One is we consider the neutrino source to be based at Fermilab and the far detector at SURF. So the same place the DUNE far detector is going to be. This results in the same baseline as for DUNE. The other neutrino source we consider to make use of the existing accelerator complex at Brookhaven National Lab. This is the accelerator needed for the RIG program and the future ERC program, and still place the far detector at SURF. This leads to a baseline which is roughly 2 times longer than the one from Fermilab to SURF. Fermilab and Brookhaven are not the only accelerator setups in the world. We also have JPark in Japan, and recently there was a study of a neutrino factory using the accelerator complex at JPark in this publication. Oops, sorry. Okay, so concerning the far detector, we assume the far detector to be basically the same as the DUNE far detector, which is going to be the most precise far detector we are going to have. Based on liquid argon TPC, we assume a total fiducial target mass of 40 kilotons, and we assume a 2.5% normalization uncertainty on the electron neutrino and muon neutrino flux at a neutrino factory. As you can see here from the expected neutrino spectrum at a neutrino factory in red, we have some neutrinos which are going to have an energy above the tau detection threshold of like 3.8 GeV or something. So there will be some, we are going to produce in some tau neutrinos in the far detector. However, we are only going to treat the tau neutrino appearance as a background and not as a signal. This is coming from the fact that it's actually kind of challenging to detect tau neutrinos. So we don't really know what exactly is the detection efficiency and so on. But we're going to learn more about that once we start actually running DUNE, because also DUNE expects to see some tau neutrinos in the far detector. So we are going to learn something from DUNE, which potentially we can also apply then to neutrino factory as a successor of DUNE. Okay, so here I'm showing sorry, the number of events we expect at the far detector as a function of the neutrino energy coming from two oscillation channels, electron neutrino going to muon neutrino and anti-muon neutrino going to anti-muon neutrino. So this is the disappearance probability. In red, this is the muon neutrino appearance probability. Disappearance is not sensitive to like different values of delta. Appearance probability, we have a change in the number of events depending on the value of delta. But what you see here is that actually there is an overlap of the events coming from the appearance and the disappearance channel. However, the disappearance channel uses antineutrinos. So if we were to able to distinguish muons from antimuons in the final state, we are able to disentangle these two channels. So this we can do that using charge identification in the far detector. And the importance of charge identification at a neutrino factory has actually been realized in the early works, where they considered a 50 kiloton magnetized iron detector as the far detector. In our modern setup, we want to ask the question if charge identification is still very important. So we consider our results assuming no charge identification, 100% electron charge identification, and 100% muon charge identification. So the first question we want to ask ourselves in the three flavor scenario, what is actually the optimal muon energy we need to maximize the precision on delta? What I show here on the left is the precision on delta in degrees as a function of the muon energy. And for the Fermilab setup, and here you see in different colors, different assumptions on charge identification. In dashed versus solid, you see different assumed true values of delta. And in gray, in comparison, I show the sensitivity or the precision of DUNE, assuming its nominal running time, so its nominal exposure of 480 kiloton megawatt years. And you see that if we have a muon energy around 5 GeV, we can improve over the precision what DUNE can do. A similar study using the Brookhaven setup tells us that the energy of the muons has to be a little bit higher, 8 GeV, and this is because the baseline for the Brookhaven setup is also larger. We also find that a good running time is to equally split between neutrino and antineutrino running time or muon and antimuon running time. However, this might change a little bit on the physics case you are mostly interested in. Then how many muon decays do you need to improve over what DUNE can do? And this is shown here on the plot on the right. Again, y-axis is the precision on delta for two different true values of delta as a function of the number of muon decays in units of 10 to the 21 total muon decays. And you see that we can improve over DUNE, shown here in gray, and even DUNE, assuming that the normalization uncertainty on the neutrino flux at DUNE gets reduced from 2-3% to 1%. If we have 10 to the 22 muon decays in total, we can nevertheless improve the precision of compared to DUNE and also compared to doubling the running time in DUNE. So for this reason, we are going to use two benchmarks in our further studies. We assume 10 years of DUNE and 10 years of hyper-K, which corresponds to these numbers of DUNE. And then we check what happens if we add 10 years of a neutrino factory, which corresponds to this 10 to the 22 muon decays in total. And again, these are the results for the precision on delta, assuming true value of delta equal to 0 or equal to -90 degrees. The different colors, these correspond to different, so these correspond to the precision, and then on the y-axis you have the charge identification ability, and you see that you see that we can achieve precisions of up to 2% on delta, assuming delta true is equal to 0, or up to 4 or 5 degrees, assuming that delta true is equal to minus 90 degrees. Yes. Okay, so why do we actually want to measure delta very precisely, and how precisely do we want to measure this phase? And a possible answer is given in our flavor models. So the CP phase predicted in certain flavor models, which try to provide a rationale behind the observed masses and mixings in the lepton sector, predict different values of the CP phase. For example, if the neutrino mixing matrix is predicted by discrete flavor symmetries and the charged lepton mixing matrix is non-diagonal, since the PM&S matrix is the product of the mixing matrix in the charged lepton sector times the mixing matrix in the neutrino sector, the measurable mixing parameters from the PM&S matrix are going to be a function of the predicted mixing parameters in the neutrino sector from these discrete symmetries and the mixings in the charged lepton sector. So different flavor models predict different values of theta 1, 2 nu. Most of them predict maximum theta 2, 3 nu. And what you see here is the prediction for cosine delta in a couple of different models. And you see the prediction for cosine delta is basically all over the place. So between -1 and +1. So if we have a more precise measurement of delta, and I show here in red what DUNE can do, we can rule out many of these flavor models. Additionally, we can also measure the other oscillation parameters very precisely, or the neutrino mass or neutrino star beta decay experiments can also additionally probe flavor models. And here I show the results for cosine delta for 4 different flavor models and the sensitivity DUNE+HK plus DUNE+HK plus a neutrino factory can achieve for these predicted values of cosine delta. And we see that the addition of a neutrino factory will improve the distinction powers of models, and we will be able to at least distinguish these 2 groups of flavor models, although distinguishing these 2 flavor models, the orange one and blue one, from each other will require even more precision than what the neutrino factory we are assuming right now can achieve. So the results for the other oscillation parameters are shown here. So delta chi-squared as a function of delta M31 squared on the left, and as a function of sine squared of 2 theta 1, 3 on the right. You see in gray our current knowledge on these 2 parameters, and you see that DUNE+HK in black in both plots will already improve our knowledge, our precision by quite a bit. But then additionally, adding a neutrino factory will improve the precision even more. And in particular, if you compare these colored lines, blue, purple, and orange, which is the addition of a neutrino factory for different charge identification assumptions, they are even improving over what doubling the running time of DUNE+HK can achieve, which is shown in dashed here. So this is a similar plot, but now in a 2-dimensional plane. So these are the results, the precision on theta 1, 3 and delta. And again, you see that the addition of a neutrino factory can improve over current constraints and also improve over the constraints what the combination of DUNE and HK can achieve. And the results for a neutrino factory can even potentially be better because we are assuming that a neutrino factory has the same far detector as DUNE. And just by running DUNE, we're going to learn a lot about liquid argon and possibly make improvements in the liquid argon technology. However, we also find that just like DUNE, the neutrino factory has only limited sensitivity to the solar parameters. So we need to impose priors on the solar parameters to extract delta and the other oscillation parameters with a high, with a good precision and with a high significance. Yes, so the addition of a neutrino factory can improve the precision on the oscillation parameters and even beyond increasing the running time of DUNE. And this is due to the presence of additional oscillation channels with the large statistics at the neutrino factory. Namely, we have access to electron-neutrino disappearance, which DUNE has only limited statistics in. We also find that the Brookhaven setup actually provides slightly stronger constraints than the Fermilab setup. And we also find that while charge identification can increase the precision on the mixing parameters, it is not as essential as previously emphasized in the literature. And this is due to the good energy resolution of liquid argon. So we can, with our liquid argon far detectors, we will be able to distinguish the muon neutrino disappearance channel from the muon neutrino appearance channel because they have a slightly different energy spectrum. So the neutrino factory is an appealing possibility, as also if DUNE and Hyper-K might disagree and further oscillation studies are required, as the neutrino factory provides a higher neutrino energy, a longer baseline in the Brookhaven setup, smaller flux uncertainty because we know exactly how a muon decays, tunable energy, and access to 6 oscillation channels and a CP conjugate ones with similarly large number of events. And this motivated the second paper where we looked at BSM scenarios at a neutrino factory. And we focus on the scenarios where a neutrino factory can provide new and strong constraints. Keeping in mind that we are going to have DUNE and Hyper-K, we are also going to have a dedicated short baseline program in the future. So we're only focusing on the scenarios where the neutrino factory can really make an impact beyond what we are going to have with the next generation experiments. So the first scenario is a kinematically accessible sterile neutrino. A neutrino factory is sensitive to sterile neutrino mass splittings of the order of 10 to the minus 3 electron volt squared, which is not surprising because that's exactly the atmospheric mass splitting. And this is also what we want to be sensitive to in our standard oscillation case. However, sterile neutrinos with these very low mass splittings are heavily constrained by cosmology, and they are also heavily constrained by short baseline experiments, atmospheric neutrino experiments, and as well as reactor experiments. So a neutrino factory is not going to provide new and strong constraints on this scenario. The next scenario are neutral current vector NSI. So these are new neutrino interactions which lead to new matter effects which scale with the baseline and the energy. Now, a neutrino factory has a higher energy and maybe even larger baseline than DUNE. So in this scenario, a neutrino factory can provide new constraints or maybe discoveries. Note, alternatively, you can also get constraints on this scenario from neutral current detection, which I recently pointed out with my collaborators. How about scalar NSI? So instead of having new vector interactions, we could also have new scalar interactions for the neutrinos. However, these effects are amplified in dense matter like the sun. So instead of you looking at long baseline experiments, we just look at solar neutrino experiments. And there recently was a paper by one of my collaborators and his collaborators where they looked at constraints from solar experiments on scalar NSI, and long baseline experiments are not going to make an impact there. Finally, CPT violation. Since a neutrino factory has access to 5 oscillation channels, which are CP and CPT conjugates of each other, the neutrino factory can potentially make an impact in probing CPT violation in neutrinos. Yeah, basically just said that. So starting with CPT violation, we are going to treat the mixing parameters of neutrinos and antineutrinos separately. So our total chi-squared will be the chi-squared for neutrinos plus the chi-squared for antineutrinos, a similar approach which has previously been used in the literature. We look at different benchmarks, DUNE with nominal running time, double the running time, and combining DUNE and the neutrino factory. And what we get is shown here. So these are a couple of plots, and these show on the y-axis the oscillation parameter for antineutrinos, on the x-axis the oscillation parameters for neutrinos. If CPT is violated, they should be different. If CPT is conserved, they should be the same. The upper two plots show different true values of delta of 0 and minus 90 degrees. Then we have the constraint of theta 1, 3, delta m2 1 squared, theta 2, 3, and the other mass splitting. And you see the constraints from DUNE, nominal running time, and DUNE, double the running time in red and blue. Then in solid and dashed, you see combining DUNE with the neutrino factory, either in the Brookhaven or Fermilab setup, and then in different colors, different assumptions on charge identification. So what we see is the addition of a neutrino factory improves the constraints on CPT violation. It also excludes degeneracies present in DUNE, which are visible here in the upper right, our plot for theta 1, 3, as well as the for theta 2, 3. DUNE suffers from these degeneracies, as you can see. However, if we add a neutrino factory, we can exclude these degeneracies thanks to the presence of electron-neutrino disappearance and muon-neutrino appearance channels. And then, as I already said before, the sensitivity of long baseline experiments to delta m2 1 squared is not great. And this is also shown here on the lower left plot. So far, we don't have any hints for CPT violation in nature. However, there is a slight discrepancy in the measurement of theta 1, 3 from solar and accelerator experiments compared to reactor experiments. So we assume that the mixing parameters for, this particular mixing parameter for neutrinos and antineutrinos is slightly different. So this is now our true value. And again, we see that if these are really the true values realized in nature, the addition of a neutrino factory allows to exclude the CPT conserving scenario and again gets rid of this degeneracy DUNE suffers from. Moving on to NSI. So this is the general framework for new neutrino interactions. It's an effective field theory framework where we have this coupling or this NSI parameters epsilon in front. We're coupling neutrinos to metafermions, electrons up and down quarks via a vector interaction. We have a total of 5 NSI parameters. The diagonal ones are real. The off-diagonal parameters can be complex, and they affect neutrino oscillations as a new matter effect. So the Hamiltonian, which governs oscillations in matter, the matter potential, or the matrix for the matter potential, now has all entries filled. In the standard model, we only have the charge current interaction, so only the one in the 1-1 element. With NSI, you fill the whole matrix, and the matter potential is proportional to the Fermi constant, the matter density, as well as the energy of the neutrinos. And this also, in the end, depends on the baseline of the neutrinos. The longer the baseline, the higher the energy, the better we can, or the larger the effect of NSI. So these are the constraints for one NSI parameter at a time. On the left, we have the constraints on the diagonal NSI parameters, where we can subtract one of the diagonal NSI parameters. So we have only two parameters we constrain, which is epsilon tau tau minus epsilon mu mu and epsilon e minus epsilon mu mu. On the right, you see the constraints on the real parts of the off-diagonal NSI parameters. Again, same color scheme, red and blue is DUNE. The different colors and the hatched regions correspond to DUNE plus a neutrino factory in different setups with different assumptions on charge identification. Generally, we see that if we add a neutrino factory to DUNE, we will improve the constraints and also improve the constraints beyond just adding more statistics. Because you see the colored blocks are actually narrower than the blue one, which is double the running time of DUNE. And the fact that the neutrino factory can improve the constraints comes from the presence of additional channels, as well as the higher energy at the neutrino factory and longer baseline for the Brookhaven setup. So you always see the hatched regions are smaller than the non-hatched regions. And this is because the Brookhaven setup has a 2 times longer baseline. We also show in black here the constraints from global fits, where the NSI parameters are actually marginalized over. And you see again that for some of the NSI parameters, future long baseline experiments are going to improve the constraints, but not on all of them, because atmospheric neutrino experiments can provide leading constraints on some of the NSI parameters. So these are the constraints for one parameter at a time. These are the constraints for 2 parameters at a time, looking at different subsets of 2 parameters at a time. Again, we see that the addition of a neutrino factory generally improves the constraints. For some combinations of NSI parameters, the addition of a neutrino factory is crucial, for example, this one here, to exclude degeneracies, and the constraints by adding, the improvement in the constraints by adding a neutrino factory are tremendous for this combination of parameters as well as for this, because in addition to excluding the degenerate regions DUNE suffers from, the presence of these 2 new channels, a neutrino factory is sensitive to improve the constraints vastly, but also for the other combinations of NSI parameters, adding a neutrino factory improves beyond just doubling the running time of DUNE. Okay, so let me summarize and conclude. So a neutrino factory is an interesting possibility as a future oscillation experiment beyond DUNE and Hyper-K, beyond Juno. We expect some improved precision on several fundamental parameters, including the amount of CP violation in the standard 3-flavor paradigm. We also expect improved constraints on CPT violation and NSI, as well as some exclusion of degeneracies DUNE is going to suffer from. And a neutrino factory could be a technological stepping stone on the way to a high-energy muon collider. Thank you very much for your attention.
Thank you very much for this very, very nice talk. Learned quite a lot. So I was wondering if there are any questions from the rest of the people in the Zoom session. I have a couple. Let's see if anybody else has. Okay, so I'll begin. So first of all, I'd like to know, in your configuration, do you assume that your detector is on axis or off axis, right? Because that's also an important thing in other setups.
Yeah, excellent question. Yeah, so we assume it to be on axis. We haven't studied like an off-axis configuration, but that is an interesting question. But yeah, we haven't studied it in this work.
Okay, super. So we have a question from the YouTube channel from Aman Gupta. asking if do we have any measurement of neutrino cross sections below 10 MeV?
Ooh, yes. Yeah. So the seventh cross sections are around the MeV range. If you want to go to much lower energies, the problem is that the cross section, that just a standard model cross section, it just drops with energy drastically. So I think it's just experimentally really hard. Also, which source of, I mean, we haven't really seen like the very low energy solar neutrino flux, for example. So we just it's challenging experimentally. So I want to say that for like very low energy neutrinos, we don't really have cross-section measurements yet. Good questions.
Okay, so usually there's a delay between what's happening here and what happens in YouTube. So maybe there might be a follow-up on
Yeah,
this.
please.
Any other questions from the organizers? Okay, so I'll proceed with my questions then. Hooray. I remember that in the old times, people also considered the golden channel and the silver channel, right? So the silver channel was like mu e to nu tau. And people assumed an emotion cloud chamber like what the one in opera or something like this. So do you think that what you're presenting would benefit from having a tau neutrino detector maybe in parallel? So how would that?
Yeah, no, that is a fantastic question. So indeed, the first oscillation studies for neutrino factory kind of did a study one channel at a time a little bit. However, we looked at all the channels simultaneously because we were using the globes framework. We nevertheless also found that the golden channel, which is muon neutrino appearance, is the channel which really drives the sensitivity to delta. So this still remains an important channel in the measurement of the oscillation parameters. Now the tau appearance channel is a very interesting one. We did take it into account as a background. We did not consider tau neutrinos as a signal, but I agree, detecting more tau neutrinos is very interesting. And as I showed on like one of the first slides, we expect actually quite a few tau neutrinos at a neutrino factory just because we have like quite a few high energetic neutrinos. One of the reasons why we didn't consider tau neutrinos as a signal, because it's not entirely clear how good the liquid argon sensitivity or like detection is of tau neutrinos. We are going to learn that by running DUNE and by all of the experiments which are preceding DUNE. So yeah, I think it would be actually very interesting to look maybe at a separate detector, like an opera type detector, to really detect the tau neutrinos. On the other hand, we are going to see hopefully quite a few tau neutrinos with DUNE. We are going to see quite a few tau neutrinos at SHIP. The question is, what are we going to learn by having a succeeding experiment detect even more tau neutrinos? Potentially quite a bit, but we have to think about that. Yeah.
Super. Thank you very much. So there's a follow-up from Mangupta, and he asks, how is neutrino factory? Sorry, let me read the question first. Okay, so how is the precision of neutrino factory regarding CP violation compared to ESS NUSB?
Yeah, excellent question. Yeah, so I did mention ESS NUSB. Let me check if I have it in my backup slides. I'm not entirely sure. Let me check. I think I removed it. Sorry. Okay, then I cannot show you the plot. Yeah, so the ESS is indeed measuring CP violation using or making much more use of the second oscillation maximum. I think the sensitivity, the expected sensitivity related to delta is going to be better than DUNE, but I don't know on top of my head if it's gonna, I mean, what the values are basically. I expect that probably a neutrino factory and ESS USB might be very similar-ish. But I mean, I cannot really give you a quantitative answer right now. But yeah, I mean, this plot is in our paper, as well as the ESS USB plots are in the ESS USB paper, so you can make a quick comparison. But I assume that it's going to be very similar. Additionally, the ESS sensitivity studies, I think they're only assuming the ESS USB, not combining with DUNE and Hyper-K and so on. Whereas here we are combining with DUNE and Hyper-K plus a neutrino factory. So the comparison might not be on totally equal footing.
Excellent, excellent. Let's see if there's a follow-up on that.
Yes.
So I was it caught my attention that the fact that you were doing this analysis on what would be the best muon energy, for certain precision to measure CP violation, I think it was. If it was better than DUNE or not.
Yeah.
And that reminded me of what happens at the plus minus colliders, that you can tune the center of mass energy. So I was wondering if you have considered something like this, of if it is possible first or to vary the muon energy, and if actually that you would profit from that.
Yes. So I think in principle, one should be able to vary the muon energy just in the accelerator setup. The other thing is we also, just from the muon decays, we do get a spectrum of the neutrino energies. So there we already have some variation in it, right? But I agree. In principle, one could think about, running, I don't know, like 5 years with like one muon energy, and the next 5 years maybe with a slightly different muon energy, depending on the physics one is interested in, the physics one wants to target.
Yeah, so in principle, I was, related to the first question regarding having it off axis, that makes the red a little bit more focused. Maybe doing something like that. I don't know if it.
Yeah, no, that's absolutely true. I agree. That might be another option. Yeah, that's good. Yeah.
Great. So okay, so Amangupta says thanks. I don't know if there's any other question from the people here.
Yeah, I have a question for Julia. First of all, the webinar was very interesting, especially all the physics potential that has the neutrino factory. But I was wondering, is any kind of analysis that can be done with these electron antineutrinos? Because usually you put the threshold, because the most interesting physics could be at with the muon neutrino. But is any other study that can be done with this extra noise, let's say?
Yeah. I mean, yes. So the electron neutrinos, the electron neutrino disappearance channel, this is an interesting channel, I think, because it gives you a different handle on some of the oscillation parameters. However, we all, I mean, DUNE also has some electron neutrinos in their beam. However, the flux is just much more reduced compared to the muon neutrinos at DUNE. Yeah, so in principle, I think it's an important channel for a neutrino factory. Especially we have the ability to look at nu E to nu mu, whereas at DUNE we look for nu mu to nu E. So this is something which is complementary. Plus, we in principle can look for nu E to nu tau, which is a channel which is extremely challenging at other accelerator experiments due to the very low flux of electron neutrinos, and then all the challenges related to tau neutrino detection. So it's just like reduction. Yeah.
Thank you.
Super. We have time for maybe one or two final questions. Let's see if there's anything on YouTube. Yeah, nothing on YouTube. And nobody here. So one last question from me. So on the old times of neutrino factories, there used to be this talk of this octant degeneracy in the measurement of theta 1,3, delta, theta 2,3, la la la. So I guess that with this large value of theta 1,3, the problem is not there anymore. But I was wondering about the degeneracy on theta 2,3, on the octant of theta 2,3. So I was wondering how would this degeneracy be solved compared to what's going to happen in DUNE and T2 hyper K, and how neutrino factories could help?
Yeah, good question. Yes. Let me scroll to the backup where I have a slide on the precision on theta 2,3. So yeah, the theta 1,3 degeneracy, it's not a challenge anymore because it's so large. We know it's 8.5 degrees. So here this is for the sine squared theta 2,3 sensitivities for the two setups, and here you see that the addition of a neutrino factory is not going to change or going to add a lot onto what we can do with DUNE and hyper K. But you also see these are three different assumed true values, these three peaks. So we are going to be able to distinguish them individually from each other. But I think DUNE already is going to be able to do that. In gray, you see that's the current knowledge. So you really don't know the octant, you really don't know the value at all. But already with next generation experiments, we are going to be able to nail down what exactly is the value of theta 2,3. And then a neutrino factory is going to add a little bit, maybe in terms of precision, especially from the Brookhaven setup, but not like drastically.
Okay, great. Okay, well, that's a shame. That is what it is. All right. So I think that we're done, unless there's Nicolas has left. So I guess that we can close the session now. So thank you very much, Julia, for this. It's been a wonderful talk. It's been a very interesting setup. And okay, Nicolas is back. So everybody, to all of the viewers, please stay tuned. In 2 weeks, we are having Kevin Kelly giving a webinar. And well, that's it. So thanks a lot, Julia, and we'll see you all next time.
Thanks.
So we are offline. Great. Ooh. Okay. Very nice.